Today we're going to talk about solving square root equations. We were talking about graphing square root functions in our last section. Now we're going to be solving square root equations. So a square root equation is an equation that contains a square root with a variable in the radicand. What we're going to be using to help solve these types of equations is the idea of being able to do the same thing to both sides of an equation, doing one thing to one side, and as long as I do the same thing to the other side, we are able to do that with our math rules. So in this case, what we're going to be doing is looking at the idea of squaring both sides of an equation to help us solve problems. So here's the key idea. If A equals B, then A squared equals B squared. And we're going to use that idea to kind of help us find some answers with our inverse operations as well to solve problems with our square root signs. So remember PEMDAS. When you're thinking about PEMDAS, normally we think about PEMDAS as exponents. Just keep in mind here that this little r that's tucked in here that some of us may or may not want to try to include in our thought of PEMDAS, this basically is just standing for our radicals. So remember back when we worked on our rational exponents, the square root of something could also be referred to as an exponent of a 1/2. So our exponents do include the radicals and the radical signs, but if you want to kind of keep that in mind, PEMDAS includes an r with the exponents just to kind of remind you that radicals are also part of that. So let's kind of look at how we're going to solve some of these equations. So first of all, we have example 1. Solve each equation, check your solution. So what we want to do first is we want to kind of isolate the square root by itself. And by doing that, we'll then be able to take a look at the whole idea of squaring both sides. So as we do usually, we undo the plus 5. We're left with x squared equals 8. So now what we have to do is we have to get the x out from underneath the radical sign. So what we're going to do to both sides is we are going to square everything on both sides. By squaring the left-hand side, the square root of x squared leaves me with what is underneath the radical sign, or just the radicand. And on the other side, when I take 8, and square it, I get 64. So that would be the solution. If I was to check this, if I do a quick check, I do square root of 64 plus 5. It should equal 13. Square root of 64 is 8 plus 5 equals 13. 13 equals 13. So that would verify that we do have the correct answer as x equals 64. Okay, so moving on to the second one. So in this case, one thing that I might want to think about here is I would like to have my square root be positive. So one thing that I might want to do here is I might want to actually move the square root of x to the other side, which I can do. The reason I might do that is that now I have just the square root of x on one side equaling 3 on the other side. You certainly could have subtracted 3 first to move the 3 to the other side to keep the variable on the left, but then you'd have to make sure you just kept the negative square root of x on the left. Well, at this point, again, we need to get the x out from underneath. So what we're going to do is square both sides. That is going to get the x out from underneath the radical, and 3 squared is 9. And when I do my check here, way back at the beginning, I'm going to say 3 minus the square root of 9 equals 0, and is that true? If I do 3, square root of 9 is 3, that does equal 0, so we do have the right answer, and that would tell us that x equals 9. Might be a better way to spin this answer around. You'd always like to have the variable on the left, so that's probably actually a better answer. Okay, so for our next example, this time we definitely have a bunch of work to do. So on this one, the very first thing when I think of PEMDAS is I want to move the plus 3 at the end. It is not underneath, so I can move it separately. I move the 3 to the other side. That gives me 16. Then I want to look at what we have. Well, I'm still trying to isolate my radical sign. So I have to think, next step here is think about dividing by 4 to move the number that's in front of the radical sign. The 2 is underneath, and I can't just move it separately. It's got to stay as part of the group. So when I move this now, dividing by 4, I'm left with x plus 2 equals 4. And here at this point, this is when I can start to say, now I want to square both sides. If I square both sides, when I think about the square root of x plus 2 times the square root of x plus 2, what I come out with is x plus 2. And then when I go to the other side to make things a balance, 4 squared is 16. So at this point, all I have to do is one more move. I'm going to subtract 2 from both sides to solve for the x. So x equals 14. To make sure that I can prove that, I guess I should do the check. We always tell you to do the check. If I plug this in, 14 goes in for my x plus 2 plus 3 equals 19. Kind of separate this out a little bit so that we see that this is the check for the problem 3. I take 4 times the square root of 16 plus 3 equals 19. And notice now we're using our PEMDAS the correct way, in the right order. Nope, I don't want that, because once I take the square root, we can remove the square root sign. But I do want to make sure that I take the square root of 16, which is 4, before I look at the plus 3. 4 times 4 is 16, plus 3 is 19. So 19 does verify. That would say that we did have the right answer for x equals 14. In our next example, we have an equation with the square roots on both sides. So right away, because I see kind of the square root radicals by themselves, and there's nothing to really move, I'm going to go right ahead and square both sides right from the beginning. And if I square both sides, that's going to free up the radicands and leave us with variables now on both sides, but at least they're out from within. Then I would think, move my variables to the same side by subtracting x from both sides. That will cancel the x's there to leave me with a 4 on the right hand side, and on the left hand side I would be left over with x minus 1. I would add 1 to both sides. X equals 5, and that should do it on that one. Okay, so squaring sometimes can lead to something that we call extraneous solution. An extraneous solution is basically something that when you do your check, it doesn't work, and it's something that we will end up throwing out. So because we do have potential solutions in this that will end up getting thrown out, it is extremely important that you check your answers, because if an answer does not work and is not possible, then we definitely have to throw out that answer, and those are called extraneous solutions. So here we're asked to solve an equation. Well, again, the very first thing that we're going to do here is going to square both sides. When I square both sides, I am now going to get x squared equals x plus 6. What's then going to happen is I'm actually going to move my x's to the other side. I get x squared minus x equals 6. And then again, I'm going to subtract it one more time, because we are looking like we have a quadratic. X squared minus x minus 6 equals 0. So we first freed it up, but we'll notice that we have x's in two different terms, that we can't subtract x squareds and x's. So we end up with something that looks like a quadratic that we just did. Well, when I focus on my factor pairs, this is one that I can certainly factor, so that's what we're going to do next. When I think of my factor pairs of -6, that will give me a +1, which is the b value in the middle. Then I'm going to get x and x. I'm going to subtract 3 and add 2. and if I use my FOIL to double check that, it would verify. So with our zero product property, we know that by setting those two equal to 0, I'm going to get x equals 3 and x equals negative 2. So it appears that we have two solutions. But we want to make sure that we do a check to make sure that we actually do have two solutions. So I'm going to go back into my original equation and do those checks. So for the first one, if I use 3's, if I plug in a 3, I end up with the square root of 3 plus 6. 3 equals the square root of 9. 3 equals 3. Check. So we know that one works fine. When I go to the second one, negative 2 equals the square root of negative 2 plus 6. Negative 2 equals the square root of 6. I'm sorry, the square root of 4. Good catch. When I take the square root of 4, I don't get negative 4. It's not saying we want the negative. It's saying we get a positive 2, which does not equal negative 2, which is telling me that this doesn't work. So negative 2 is actually going to be an extraneous solution to us. So with that in mind, we actually have to cancel this one out. And we want to make sure that we say here our solution is x equals 3. So the negative 2, by doing the check, gets thrown away because it does not work even though it looks like it should. Okay, and here we have one more example. We're talking about the period which we use with the capital P in seconds of a pendulum that is given in the function P equals 2 pi times the square root of L over 32, where L is the pendulum length in feet. What is the length of a pendulum? It has a period of 2 seconds. So basically, we know a pendulum is what would be swinging back and forth. The pendulum would swing, a period would be all the way back and all the way forward again. That's what the function is given to us. So we're just going to use that function to kind of plug it in. Now what we are most interested in is trying to figure out what is going on at 2 seconds. Well, they told us that P is the period. And we were told that the period is, we want to know at 2 seconds, what is the length? So this is the other piece. What is the length, which is the L we're looking for? So once I've determined that it's the P for that one I have, the length is what I don't have, now I can just plug in my formula and solve. 2 pi, the L is what we don't have, and 32. So my first move is going to be the following. I want to get the radical by itself, so my very first move is to divide by 2 pi. And notice how I don't want to change this into 3.14 because it's just going to make a crazy decimal and make this kind of a mess. So when I divide 2 by 2 pi, notice that that's going to give me 2 over 2 pi, which I can reduce to make 1 over pi, just to make it a little more simple. The 2 pi's cancel each other on the right-hand side and leave me with L over 32 under the radical sign. This is where I want to think about squaring both sides. So I put my little square on both sides, and then I can follow through. It's going to give me now 1 squared, which is 1 over pi squared. And on the other side, now we've freed up the expression underneath, or the radicand underneath, to get it to be L over 32. So at this point, what I'm trying to do, remember, is we are trying to isolate L. That's our ultimate goal here. So at this point, what I do next is I'm going to multiply both sides by the 32, and that will get the 32 from the right-hand side to cancel the 32 in the denominator, leaving us with L, which is what we're really looking for. On the right-hand side, when I multiply 32 times 1 over pi squared, I get 32 over pi squared. Well, again, we probably really wouldn't leave an answer as 32 over pi squared. So this is where your calculator comes in, and we would run our calculator numbers, and we would say that L is, let's make this more of an approximately, L is approximately 3.2. So the pendulum length is approximately 3.2 feet. So again, by leaving the pi symbol as long as we could, it actually made a very complicated looking equation, not that difficult. We just need to make sure we thought through it and worked through all of our steps. So just remember, when you're solving these square root equations, you're going to be squaring both sides at some point to help free up the radicand from the radical sign. Just make sure that you are isolating that radical first before you do the square root of both sides, the square of both sides, and then you can solve using your PEMDAS and also then your SADMIP steps as well to isolate the variable you're looking for.